Hello folks, it's time for another Murphy video, this time on section 3.6, perpendicular line theorems. There's really two halves to this section that are kind of different but with some overlapping ideas between them. The first one just deals with seemingly random perpendicular line theorems that are used mainly for some computations, and then the second half involves a process that we're going to have to talk about. It's going to require some thinking, and it actually has some algebraic properties that we might want to use in order to come to some conclusions when laid out with a certain kind of diagram. I know that sounds kind of unclear, but you'll recognize what I'm talking about when we get there. First, let's talk about some of these perpendicular line theorems, and let's actually demonstrate one with a proof. One of these theorems says, essentially, if I have two angles that are a linear pair and they're congruent to each other, then the lines that create them are going to be perpendicular to one another. So essentially, if I'm given this diagram, here's 1, here's 2, and they're congruent, then it's going to be the case that G and H are perpendicular. So again, when you approach a proof, you should be thinking about it from the perspective of how can I justify every conjecture given either the previous things or some given piece of information or something I can deduce. Basically ask yourself why. Why this, why that? So let's start with the notion that 1 and 2 are a linear pair. Why? How do you know that? Because it's given to us. It's one of our givens. So we can safely assume that it's true for the sake of doing something with this problem. So if I say that 1 and 2 are a linear pair, and then I say that 1 and 2 are supplementary, and if you would ask yourself, how do you know that they're supplementary? Well, the answer is because that's what it means to be a linear pair. If two angles are a linear pair, then they're supplementary. That's the linear pair postulate. And again, I'm not going to be too worked up about the wording here. If you just note that it's because they're a linear pair. Technically, definition of linear pair wouldn't be correct, but I'm not going to bust any chops about it. But like you get it. Being a linear pair means that you are supplementary. And what does being supplementary mean? It means that the sum of your measures is 180 degrees. So how do we know that the measure of 1 plus the measure of 2 is 180? Because as the previous line suggests, they're supplementary, and that's what it means to be supplementary. Cool. So right now we're at a point where we have an equation, which is good. Let's hang on to that. 1 is congruent to 2. We know that because it's given to us. So how do I know that the measure of 1 is equal to the measure of 2? Because that's what it means to be congruent. That's the definition of congruence. So fine. Here I have a couple different endpoints. Like I kind of got here and then stopped, and then I got here, and this is a different conclusion from a different given. So how do I put those two together? If 1 plus 2 is 180, and 1 is 2, well then, it looks like I can take the measure of angle 2 in the first equation that I have here, and substitute the measure of angle 1 because they're congruent. So now I have the same equation for line 3 as for line, where am I, 4, 5, 6? But with the measure of angle 2 subbed out, and the measure of 1 subbed in. So what I can do here is I could say, again, this is a substitution property, measure 1 plus measure 1 is 2 times the measure of 1. We'll call that combining like terms. And then from here, it's easy to see that I basically have just like a normal algebra problem. You can think of this like 2x equals 180. You divide each side by 2, and you get the measure of 1 equals 90. This is straight up arithmetic, and we cite division as the reason. I guess technically you could say you multiplied by 1/2, so I guess technically the multiplication property is right, but whatever. So 1 would have to be a right angle then, because if its measure is 90, that's what it means to be a right angle. And if ever your justification is that's what it means to be blank, typically it's going to be definition of that thing. So from here, if 1 is a right angle, then I can conclude that lines G and H are perpendicular, because again, that's what it means to be perpendicular. It means to intersect to make right angles. So that's it. That's some theorem that we haven't given a name. And you know what? We're not going to give it a name either. Our book refers to it as theorem 3.8, and this is the thing that we just proved. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. In other words, if I take each of these theorems and break them down into if-then statements, I can say if 1 and 2 are congruent to each other, then ray G is perpendicular to line H. By the way, I know we sometimes cite theorems in our proofs. I'm never going to make you remember that this is theorem 3.8, and this one's 3.9, and this one's 3.10. That's like arbitrary bullcrap stuff to remember. That's not important. There's no good reason for it. So don't just remember the ideas. Don't remember what the ideas are called. You're never going to see these in proofs. You're only going to use them for solving things. And some of them are very intuitive, like this one. If two lines are perpendicular, then they intersect to form 4 right angles. So in other words, if A is perpendicular to B, let's assume straight off the bat we know that that means that this angle's right. How can I conclude the rest of them are right? Well, for example, if 1 is right, I know 4 is because of the vertical angle theorem. I know that 2 is because they're a linear pair by definition. If one of them is 90, 90 plus something equals 180. This also has to be 90. And then the vertical angle with 2 is 3, and vertical angles are congruent, so 3 is also 90. Holy smokes, to nobody's surprise, one right angle implies that they're all right angles. Fine. If A is perpendicular to B, then 1 and 2 and 3, and also 4 are right angles. The last theorem on this page, theorem 3.10. If two sides of two adjacent angles are perpendicular, then the angles are complementary. So I have angle ABC. I know that AB and BC are perpendicular to each other. I know that a ray goes through this. I'm not going to say bisect, because that would imply that 1 and 2 are congruent, but we don't know that. Let's just say a ray goes through this and cuts up this 90 into two angles. Well, I could use the angle addition postulate to say that 1 plus 2 is still equal to 90. They'll still give me this 90 degrees. So what does it mean when the sum of two angles is 90? That is, by definition, complementary. So I can say that if these two are perpendicular and something cuts through the 90, then the remaining pieces of that cut, that intersection, are complementary. Two more random nameless theorems. Oh, actually, no, these do have names. Sorry. Perpendicular transversal theorem. So we know what it looks like when a line cuts through two other lines. We call that line, in this case J, a transversal. So maybe this will save us some math, some time in the future. Maybe this is something that we've actually deduced before because I've given you similar problems. If a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other. So for instance, H is parallel to K, and also J is perpendicular to H. That means that if this is given information and this is 90 degrees, I want to then somehow conclude that this right here is also 90 degrees, because that would imply that J is perpendicular to K. How can I do that? Well, the relationship between this angle on the top right and this angle on the top right of this intersection of 4, if they're both in the top right of their intersections of 4, that implies that they're corresponding. So since these lines are parallel, corresponding angles are congruent, so 90, 90. And then if this guy down here is 90 degrees, then guess what? J and K, by definition, are perpendicular. Notice how I'm kind of just talking these ones out and not doing full-on, like, two-column proofs? Even though you would expect some of these ingredients, like corresponding angle postulate, to pop up if it were a two-column proof. Last one. Lines perpendicular to a transversal theorem. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. If two lines are perpendicular to the same line, so M and N are both perpendicular to P. That's our given information. So how does that mean that they're parallel to each other? Well, here's where I could actually invoke a converse theorem and say that this 90 is congruent to this 90. So because corresponding angles are congruent, the converse would say if corresponding angles are congruent, then the lines are parallel. So whereas up here I had the lines are parallel, so these are both 90, here I have the converse. These angles are both 90, so the lines are parallel. That's the top one is the corresponding angle postulate, the cap, and the one below it is the cap converse. They allow us to do similar but kind of different things. So again, in a conditional form, if M is perpendicular to P and N is perpendicular to P, then M and N are parallel to each other. And with the diagram, it makes it extraordinarily obvious. So these are properties that you'd probably want to invoke when you're solving for things like some textbook problems, but like I said, the second half of this actually involves a kind of algebraic approach to something. Suppose I give you a problem like this. I got big boy Mario here, whose gut protrudes 2 feet out. Will he fit if he goes down feet first in this pipe? So basically, I want to take this 2-foot wide boy, slide him down this pipe, and then wonder if he's going to get stuck anywhere. So we should ask ourselves, basically, how wide is this pipe? Is it 2 feet? Take a second to actually consider and think through and think about how you would justify your yes or no here. Maybe actually pause it for a couple seconds, think it through, and then I'm going to give the answer. Stay hydrated, guys. So the answer here, well, let's actually first talk about a common misconception. I'm sure what a lot of you will do is say from here to here is about 2.5 units. 2.5 is bigger than 2, so he can slide down here no problem because he fits. With about 6 inches of gut space left. This isn't quite correct. And I think if we maybe rotate our iPads, if you're on your iPad, or just tilt your head such that it looks like these 2 green lines are horizontal, then it makes it obvious. Why? Because essentially what you've done, if you've taken this approach, is you've said, here's the top part of the pipe, here's the bottom part of the pipe, and the distance between them, if I draw it out like this magenta line, when everything's tilted so that these are horizontal, it kind of looks like you're looking at this. Like it's not a straight-on distance. If I asked you to find the distance between these two lines, what you'd presumably do is go with the height when it's laid out horizontally. So what's the difference between this dashed line and this crooked one that you've drawn? Like, why do I go with this vertical one rather than this crooked one? Or like this crooked one, or this crooked one? Presumably, and it's obvious in this case, that if I'm looking at something horizontal, the distance between two horizontal things would be a vertical line, because the relationship between vertical and horizontal is one that is perpendicular. So here's the key to finding the distance between any two lines on the coordinate plane. We need that distance to be perpendicular. So let's just off to the side draw what we would expect to see off the coordinate plane. Here's one side of the pipe, here's the other side of the pipe. We want to calculate the distance of a segment such that that segment is perpendicular to both of these things. If it's perpendicular to one, it's going to be perpendicular to the other because they're parallel lines. So how do we find the length of a perpendicular segment? How do we draw a perpendicular segment? Where do I draw it, first of all? If we're on a coordinate plane, which we are, you should be remembering that things that are perpendicular have opposite reciprocal slopes. So the slope of this guy, the slope of the green line, is, let's just count. From here to here. That's down to right 1. So that's a slope of -2. Makes sense. The pipe's going down at an angle, and a rather steep one, so -2 makes sense. So what should the slope of the distance segment look like? If it's perpendicular, then we would expect it to have the opposite reciprocal slope. So let's say slope of magenta, m of m. The opposite reciprocal of -2 is +1/2. So you know what? Let's pick a point on this line. How about the origin? Such that it's easy to see this point, and then go up 1, right 2. Up 1, right 2 puts me here. So I've created a perpendicular segment. And this segment is going to be representative of the distance between these two lines. So we actually need to find, now we need to calculate the distance, right? How do I find the length of a segment? Ask yourself, because you've learned this before. How do you find the length of a segment? We did this way back in chapter 1, except back then, let me actually clear everything else out here. Back then, actually, the question was, how do you find the distance between 2 points on a coordinate plane? The length of the segment is the distance between this endpoint and this one, right? So I could actually do this. Let's call this D for distance. I could do this by using the distance formula, or we talked about another way. The other way was to set up a Pythagorean theorem situation, where if I just draw out the horizontal line from one endpoint to the other, and also the vertical line, I now have a right triangle, and I could use the Pythagorean theorem. This leg is length 2, this leg is length 1, so d squared, in other words, c squared, equals 1 squared plus 2 squared. Again, this is basically just a squared plus b squared equals c squared. So d squared equals, this is 1 plus 4, which is 5, so d is equal to the square root of 5. Which you should have some idea of what that is. It's a little bit bigger than the square root of 4, so it's a little bit bigger than 2, so we know that we're in the clear. But if you take a calculator and you find the square root of 5, it is, here's a situation where we want to round it, because it makes sense contextually to round. It's like 2.24. So, since the distance, or the width of the pipe, the distance from one part of it to the other, since d is greater than 2, the answer is yes. Yes, Mario fits. You could have also concluded that Mario fits from the get-go if you did it wrong by going from 0 to 2.5, and you got it wrong by accident, which is going to happen when it's a 50-50 yes or no situation. But hopefully you took away the idea here, which is if we're going to find the distance between two lines on a coordinate plane, we need to first find a perpendicular segment that would demonstrate this distance, and then we should find the length of that segment. I also want to note, if I put the segment somewhere else, like maybe like right here, if I go right 2, up 1, or like up 1, right 2, I still end up with the same answer. So it doesn't matter where we put the perpendicular segment, it's going to have the same length, it's going to be perpendicular no matter what. I just went down here. So I would suggest making sure that an endpoint that you choose actually has integer coordinates, so that finding the distance is easy. So the takeaway here, the distance from a line to a parallel line, which is what we just did, or a point, which is what we're going to do on this page, is going to be the length of a perpendicular segment. So for example, suppose I want to find how far away from this line this point is. And again, if I rotate this until it's sideways, what I essentially end up with is this line being horizontal and this point being, I don't know, just like somewhere above it. Or below it, depending on how you rotate this diagram. But if I rotate it counterclockwise, such that M is horizontal and P is above it, if I want to find the distance, I'm not going to do this. I'm not going to say this is the distance from P to line M, right? I'd want to go with this. This perpendicular segment would indicate, or would be representative of the distance from the point to the line. You just go the shortest distance, which implies a perpendicular segment. So fine, how do I do this then? Given that I'm talking about perpendicular things, I should find slope. This has a nice easy slope of 1. The slope of line M is up 1, right 1, seemingly. So I can say the slope here is 1. So what is the slope of a perpendicular segment, which I'm going to draw in blue? And I'll call it, I don't know, B. B for blue. The slope of my blue perpendicular segment is going to be the opposite reciprocal of 1, which is -1. I hope you can understand why. So if I look at P, and I look at the line that has a slope of -1, it's going to intersect M somewhere. And my task now is to find the distance from P to this point of intersection. So here's what I see every year. People eventually say to go from P to the line, I go 1, 2. 2 diagonal units away from corner of the box to other corner of the box, that's 2 units. No, that's not how it works. We know how to do this. We should do this the right way, which is to say, well, again, if I treat this like D, and then I look at this like a right triangle where here's the horizontal difference between the intersection of P, and here's the vertical difference. This is 2, this is 2. So A squared plus B squared equals C squared, where C is the hypotenuse, which I'm calling D. 4 plus 4 is 8, so 8 equals D squared. So D, if I square root both sides now, is equal to root 8. Which, yeah, there's a bunch of ways you could represent this. If you know how to simplify radicals, then you know that this is 2 root 2. If you want to round this, I'm going to get my calculator. You know that root 9 would be 3, so root 8 is a little bit less than that. And yes, it comes out to approximately 2.83. If ever you're going to round, at least go like 3 units to the right of the decimal. At least give me the hundredths place. But any of these is fine as a final answer, provided you actually showed all the work leading up to it. By that point, I'll know that you know what you're talking about. Let's do one more problem, then maybe one more proof. Yeah. So, how do we know the blue segment is the shortest distance between the purple lines? Again, in this case, before I start answering questions, I would suggest that you pause it and try on your own, but I'm going to go for it. The distance between the purple lines. So let's actually write this out. The slope of the purple lines are each -2. That is down to right 1. -2 and 1. And it is important to note that these purple lines actually are parallel to each other because they have the same slope, and clearly clearly a different y-intercept as each other too. Because if these lines weren't parallel, then by definition they're going to intersect somewhere, and if they intersect, then the distance between them is 0. So this whole distance between lines things only really works if the lines are parallel to each other. But yes, this top purple line also has a slope of -2 as well. So then how do I check to see that this blue segment actually is perpendicular to it? Let me clear a lot of this out here. Sorry, I think I just gave it away. How do I know that it's the shortest distance between the purples? Well, as I've been saying this whole time, the shortest distance between any 2 parallel lines is going to be a perpendicular segment. So how do we know that the blue is perpendicular to the purple? We compare the slopes because we're on a coordinate plane, so that's how we do that. Let's see. I'll choose any one point on the blue line, any other point on this blue segment here, and I'll count. It looks like my ratio of rise over run is up 1, right 2. So that is a slope of +1/2, and +1/2 is perpendicular, or is the opposite reciprocal of -2. So I could say blue is perpendicular to purple, and I'll just note opposite reciprocal slopes. Except I'll trim it down. Right, because one is 1/2, and then the other is -2. Cool. So what is the distance now? Well, if I want to find the distance between the two lines, I will use this perpendicular segment in order to find its length. We know how to do this. I hope we know how to do this. Again, I could take these coordinates and shove them in the distance formula. Fine. But that's almost never going to be the best way to do it, especially when you're looking at a diagram. I would always advocate for using the Pythagorean theorem. D for distance, -1 to 5, as far as the x-coordinates are concerned. -1 to 5 is 6 units. 2 to 5, as far as the y-coordinates are concerned, is a distance of 3 units. So I could say 3 squared plus 6 squared equals d squared. That's 9. That's 36. 9 plus 36 is 45. And then you square root both sides. You get d equals square root of 45. Which, yes, you can leave it like this. You could, if you know how to reduce, which if you don't, that's fine. This does reduce to 3 root 5 if you want to approximate this. Root 45 is a little bit less than root 49. Root 49 is 7. So root 45 would have to be 6 point something. I just jammed it in my calculator. It's like 6.71. So again, any of these are fine here. The important thing to know, the important takeaway from the second half of the section is basically the distance between two lines, or any line and a point, is going to be the length of a perpendicular segment. You do slopey stuff, and you do the Pythagorean theorem in order to find out what that distance is. Just one more thing. There were some theorems at the very beginning of the section. One was the very first one that I proved with a table. I figured we could also prove this one just for some additional proof practice. And I'm just going to go at it because it's really not even that long. Ready? If I want to show that these two lines being perpendicular implies that angles 7 and 8 are complementary. And in the theorem there were 1 and 2, but it doesn't matter. Let's go one step at a time. ED is perpendicular to EF, because we're told so. The two rays are perpendicular, as the diagram indicates and as the given says. This implies that DF is a right angle because being perpendicular implies that you have right angles. That's literally what it means to be perpendicular. And along that same line of thinking, there should be a degree sign there, DEF measures 90 degrees because that's what it means to be a right angle. And again, that's what it means to be blank, implies that you are evoking the definition of that thing. So then, let's put this aside for a moment and move on to another piece of information here that we can deduce. The measure of 7 plus the measure of 8 equals the measure of DEF. Looks like it's saying this part plus this part equals the whole thing. The sum of the parts equals the whole, when we're talking about angles, is the angle addition postulate. But what that previous step that I temporarily abandoned for a moment, what that gives me is it allows me to say that the measure of DEF is equal to 90, and I could substitute one for the other in this equation. And now suddenly I have an equation that indicates that the left side means 7 and 8 are complementary. How do I know that? How does 7 plus 8 equaling 90 mean the angles are complementary? Because that's what it means to be complementary. So a lot of definition stuff here. I know it's very tedious. I'm not going to expect you to do proofs like this. I'm not going to ask you to prove theorems too often because they typically are tedious. But mainly the theorems that we discussed in the first half, the purpose of those was for you to use that information for solving things. And the textbook has some problems where you'd want to do as much. So okay, I think that's actually all the important stuff in this video, and it's running long enough, so that'll do for now. Thanks for watching.